Okie dokie. So, we're going to continue talking about virtual memory today. I think that it's probably good that we're going to have a little bit of review since we have skipped two lectures now, or two classes. So, probably need to have a little bit of a refresher. But remember that the neat thing, I mean, we talked about virtualizing the processor, and that was clever. We didn't need too much hardware support. We needed a way of interrupting the currently executing program, so we needed a way of having some kind of hardware interrupt that we could trigger. We needed some way of preventing processes from seeing each other's state and manipulating the hardware in specific ways. So we introduced protection levels, and so that was all cool, but it wasn't really a big change to the way that the hardware works. But virtual memory, like being able to virtualize the address space of different programs, required a pretty significant addition to the way that our processor worked. Remember, we had the memory management unit, and instead of just sending physical addresses out from the processor to memory, now we have a mapping table that allows us to map each virtual address through the mapping table into a physical address. And so this was a pretty significant change, and you'll notice that we have to introduce quite a bit more machinery to support this in the hardware than we necessarily had to for doing the process abstraction. So anyway, so memory is divided up into pages of some power of 2 size. On IA32, it happens to be 4 kilobytes, which seems to work out pretty well. And so you can see, yes, it's much larger than 1 byte or 1 word because we want the page table that maps virtual addresses to physical addresses to be manageably small. We don't want it to be unnecessarily large. And so, yeah, we map each virtual page to a physical page frame, which is the physical memory that's actually plugged into your computer. And page table entries are the things that do the mapping. So we talked about this, how it has to be in hardware. MMU, you're going to be hearing MMU a lot over the next couple of weeks because it is a central fundamental component to this whole virtual memory abstraction. And in fact, a lot of, when you look at the way an operating system works, the stuff that lives in the kernel, providing the process abstraction, a lot of its work centers around managing the memory management unit, configuring it so that we can have this process abstraction. So that's a thing that does the translation. This is the way that it works. Remember, we had the page table base register on IA32, but it's just the thing that says this is where the page table is. We use the virtual page number to index into that thing, and the entry is the physical page number that we can then send out to the memory. Now, the offset within the page can come across directly because the virtual pages and the physical pages, or the physical page frames, are the same size. It wouldn't make any sense to have them be different sizes. So the offset comes across. The virtual page number is just using it as an index to look up the physical address. Okay, so that's all pretty easy. Now, there were things that we like. Now, we suddenly can do a whole bunch more. We can do shared memory, shared libraries, which is really nice. It saves us a ton of memory when we have many programs using the same library, which happens all the time. You can, I mentioned the C standard library, but you can think of SSL libraries. If you have operating system APIs that everybody is using, then you have those loaded into shared memory region. We have process isolation. We just give each process its own page table. And context switches are really fast because we just switch page tables. We don't have to copy anything anywhere or anything like that. Now, the one thing that we started talking about last time, which was, again, two lecture slots ago, is that we still have the problem that we're constrained to the amount of physical memory that our system has. Even if we have a process that's stopped and been stopped for a while, we can't really use that memory for anything else. And so what we'd like to do is start applying some of our caching notions to virtual memory so that instead of virtual memory being this thing that controls physical memory or just controls the perception of physical memory that processes have, now we're going to start making virtual memory a cache of data that's actually stored on the disk. So now the disk size is going to be the limit of our virtual memory space, or how much memory we can hand out to processes, not the actual physical memory that we have. Okay, so we had level 4 in our little thing. I mean, it's not like you're going to walk into some place and they're going to have documentation that says L4, L5, and stuff like that. That's just using the memory hierarchy that we've described thus far. Okay? So main memory is level 4, and it's a cache for the disk which is the L5 memory. Okay, so we have to have some way of keeping track of things, and we'll just reuse our cache concepts, except you'll notice a slightly disturbing reality that things are given different names, and so you kind of have to, it's like more languages in your head. You just have to keep track of the multiple names for things. But our page table entries need to have a few more details. We need to know, is a page frame actually assigned to a virtual page? We have to know that. So we need to know, does the virtual page, or I should say the address range represented by a virtual page, does that correspond to some actual data, or is it unassigned to the process? Because if it's unassigned, then we know that accesses in there are just invalid. But if it's in there, we may need to do something special. Also, is a virtual page cached in DRAM main memory? So is it valid, or is it present in main memory? We need to be able to keep track of that stuff. Once we do this, and you'll see that it's pretty straightforward what we add to our page table entries and the MMU's functionality, you'll see that now we can start handing out a lot of memory. We're not limited anymore by our physical memory size. We can actually start having a lot of space available. And like I say, we can use our caching techniques. If the programs are behaving well, we have good locality, then we should actually see pretty close to DRAM speeds, or even better, for our program memory accesses, even though we're actually storing the data ultimately on the disk. Okay, so this is the reality. DRAM access latency used to look horrible, 100 nanoseconds. Now it looks really awesome because it's 100 nanoseconds as compared to tens of milliseconds. So cache misses, if you will, we actually call them page faults, but a cache miss at this level is incredibly expensive. We don't want to have misses if we can possibly avoid them. We also note that disk throughput is much better than the latency. Okay, so once I actually find that byte of data on the disk, well, that was slow. That's the thing that takes a few milliseconds. But once I get there, I can read a bunch of data really fast. The throughput is at least 50 meg. I shouldn't really say that because my last laptop, the disk throughput was like 40 megabytes per second. You can measure this stuff. It's not very exciting, so who cares? But if you're curious, you can definitely measure it. But anyway, so once we have found the data, we can read it really fast. So if we have a transfer unit of 1 byte, then a miss is going to cost 8 to 30 milliseconds. But let's say that we want to transfer 100 kilobytes instead. Well, all of you can do the math. It's not very complicated. We just add in a couple milliseconds. So you can see that it's not that much more expensive to get a bunch of data versus getting a single byte. And so this also factors into, hey, why don't we use pages that are larger than 1 byte? And why don't we make those pages actually some significant size? Okay. So I say large. It is large when you consider it from a caching perspective, because so far our cache lines have been 64 bytes. But we're going to pick a page size of 4 kilobytes because that's what IA32 does. Other systems might have different sizes, but they tend to be relatively large because getting those extra bytes really only adds on a few microseconds to the overall hit time, or I should say the miss penalty. Also, we can use really sophisticated policies because we're in software. We have tens of millions of clocks if we have a miss. And even if we have a hit, we have some number of clocks. So we can go ahead and spend a little bit of extra time to make sure that we avoid misses if we at all can. So, like I say, the DRAM cache is going to be fully associative. And also, we'll make sure to write back later, because if some program is writing to a page, a good presumption is that it's going to continue writing to that page. And so we'll keep it around and just write it back to the disk when we actually need to evict it. And so if you ever had a parent who has a disturbing tendency to turn off the computer without actually shutting it down cleanly or anything like that, I certainly have had those experiences. This is yet another reason why we need the OS to shut down cleanly, because we may have data that's in memory that needs to be written back to disk before the system is shut down. And so this is yet another one of those things that has to take place before the OS can actually be terminated. Any questions so far? All right, so page table entries. We talked about how we need to enhance them. Before we just said, hey, this is an entry that says this is the physical page number corresponding to the virtual page number. So now we'll add a valid bit that says whether or not the page is present. Okay, so yeah, valid is, if valid is 1, then the page is cached. And if it's 0, it means it's not cached in DRAM. Now you'll notice that we have a new thing. Because we still have the physical page number, we still have to have something in there. And so we have a couple of options now. If valid is 1, that address can be used directly by the MMU to do the address translation. But if valid is 0, we can still use that address to represent something else. And this is what operating systems do. If valid is 0, then they'll use that address in there to say, this is where on the disk this data is stored. Okay? So you see here, if the address is not 0, the virtual page is allocated, and the address is the page's location on disk. If the stored address is 0, so the valid bit is 0 and the stored address is 0, we know that this address range is simply not in use. Okay? So we can represent different things by using these bits. Okay? And this does have multiple names. In fact, this is one of the things that kind of sucks about assignment 8. We call it valid, IA32 calls it present, and the assignment calls it resident. But they all kind of mean the same thing. Trying to develop your plasticity, mental plasticity. So valid, present, resident just means that the page is in memory or not. Okay, the thing about this virtual memory facility, we have the MMU, and it's able to do address translation all by itself because we need it to be fast. Remember, memory accesses are one of the most commonly done things by programs, and we want it to be as fast as possible. So we have hardware to do it. But the problem is that we run into situations where the processor is simply unable to deal with all of the situations that can arise. So the MMU does as much as it can, but there's situations that arise where the operating system has to get involved. So like you see here, what to do when a virtual page is not in main memory? What if that valid bit is 0? What do I do? I don't know. I don't know how the operating system is written. So the CPU can't do anything by itself to resolve that. So the OS has to provide the appropriate interrupt handlers to handle faults and other issues that arise when the MMU says, I'm sorry, I'm unable to complete this operation. Okay? So this is probably one of the most important places where the hardware interacts with the operating system, and the interaction is very sophisticated and it's really cool. I love this. I'm trying to think. I think it's probably in the third assignment you have to build a virtual memory system in CS124, and it's really neat stuff. So it's complicated, but it's really neat when it's all working. Okay, here's a really simple example. We have a virtual memory here where we have 8 virtual pages. I mean, we're just like swimming in the memory here. And we have 4 physical page frames, which I'll also just call physical pages for simplicity. But you can see that the physical memory holds various virtual pages. And our page table says which ones are in memory, in physical memory, which ones are not, but also, if it's not, is it actually an allocated page or is it a page that is unallocated? If it's allocated, it says where it's stored on the disk. Okay, so some virtual pages are cached in DRAM, right now 1, 2, 7, and 4. Some pages are only stored on disk. So 3 and 6, you can see the dotted lines are to pages 3 and 6. And 2 pages are not yet allocated. So in this case, 0 and 5 are not yet allocated. So if the program accesses a word in page 2, okay, how do we know it's in page 2? Well, we throw away the offset bits and we look at the virtual page number and the address. So it's really simple. You're all familiar with that from assignment 5. Assignment 5 was really hopefully straightforward in that way. But we can use that as an index into our page table and we say, hey, PTE2, yay, the valid bit is 1. The MMU can handle it all by itself. It doesn't need any intervention from software at all. It can just go. It's going to be as fast as possible. So it just translates that out to physical page 1, if I can follow pointers correctly. Yeah, and so the MMU sends out physical page 1 with the virtual page offset attached, and then it just does the memory access. And we're done. Super simple. Now, if we had a situation where it accesses a word in virtual page 6, you can see it's a little bit more complicated. The MMU says, okay, I'm going to throw away the offset. That tells me that I'm in virtual page 6, so it goes and looks at PTE 6, and it says, uh-oh, the valid bit is 0, so I'm not able to actually do this address translation. Operating system, help. It says, I need help. It goes ahead and triggers a fault to say that it needs help. And so this is a page fault. There's several different kinds of faults, and this will actually kind of become really important. So we'll try to spell this all out really clearly. But in this scenario, we get a page fault because a memory access was against a page that's not currently in memory. So the kernel has to provide a fault handler. And like I say here, the kernel is the thing that manages the page table and these memory pages. So it can basically decide, did I allocate a page for page 6? Do I need to move it off the disk and back into physical memory? Or is this just a bum memory access and I need to tell the program to shut down because it did something invalid? Okay, so the kernel is the thing that creates the abstraction. The kernel is the thing that decides how to handle these situations. So in our situation, the kernel is invoked, and the kernel goes in and says, yes, the valid bit is 0, so I was triggered properly, but there's an address, so this must be a page that's just in swap right now. So it goes ahead and loads that page into memory. So we have a bit of a problem, right? What physical page do we load it into? Kernel has to make a decision. Kernel has to pick somebody. We have this whole thing of we need to pick a victim, and we need to evict them, and we need to free up that space. And obviously that can be challenging too, because what if that victim is dirty? Well, then we need to write it back to its corresponding place in the virtual memory stored on disk. So we need to go through this whole process. Why did it choose virtual page 4? I don't know. It just did. Okay, we just chose one. So virtual page 4, my favorite eviction policy is random because it's easy to implement. So you just randomly pick someone. You go. And it's not very good, it turns out. So anyway, you pick virtual page 4. If it happened to be modified in memory, then we need to write it back to disk. If it's not modified, we can just throw it away because who cares? And the page table entry for virtual page 4 also gets updated to say this page is no longer resident. It is now not in physical memory anymore. Okay. Now the next thing that happens is the kernel now has an empty frame, so it can load virtual page 6, which is the one that was accessed, load it into that physical page, and then change the page table entry for virtual page 6 to say, hey, it's valid now, and here's the physical page that it stored it. Okay. So all of those things happen. Now the kernel returns from the page fault handler. Where does it go back to? The correct answer here is the faulting instruction, because remember, this is a fault. Traps go back to the next instruction. Interrupts go back to the next instruction. Faults go back to the faulting instruction. Aborts go nowhere. Okay, so the fault goes back to the faulting instruction. And so the program repeats its attempt to access virtual page 6. And this time the MMU looks at page table. It goes through the exact same process. It really is that uncreative. And that's fine. That's exactly what we want. So the MMU says, entry 6 in the page table, or index 6 in the page table, hey, the valid bit is 1. I can handle this. So it takes the physical page number, appends the virtual page offset, sends it out, and the physical memory access is performed. Any questions? This is really key. You'll basically have to implement this mechanism in assignment 8. Okay? It's really cool when it works, and it's really frustrating when it doesn't. You'll see why. So, okay, now if we have a situation where a process is like, you know what, this amount of virtual memory that I have is nice, but I'd really love to have more. My heap is growing, my stack is growing, whatever. Then the kernel can basically allocate more virtual pages to that process. And really what that means is, hey, I need to allocate more space on the disk because now DRAM is a cache for space on the disk. So like I say here, if the process said, I really want more space, and the kernel says, okay, I'll give you virtual page 5. That was previously unallocated. What it can do is just say, here's where it is on the disk. So it updates the page table, but it doesn't have to necessarily page it in or mark it as valid or anything like that. It can basically say, you know what, program, you said you needed it, but I'm not going to actually take up a physical page frame with it until you actually access it, and then it will load it. Okay. So yeah, the point where the program begins to use virtual page 5, that's the point where it'll actually be loaded into physical memory. Now there is a little note here, which is, I guess, important to mention, in that the virtual memory stored on disk, or our swap file or swap partition, depending on the operating system implementation, does not have to maintain these pages in order. You know, there's all kinds of constraints that you could try to create. You can be very clever in how you manage swap space, and most operating systems try to be clever so that they don't take up very much space with it. Okay. There's various benefits and drawbacks to swap files versus swap partitions. We talk about those in the OS class, but we don't really go into them here. Okay, any questions? It's pretty neat. Okay, so now, like I say here, DRAM is a cache to virtual memory on disk. This is the thing that's a little bit annoying. This virtual memory paging stuff has slightly different terminology than hardware caching, because hardware caching kind of came along a little bit later when we actually had multiple cool technologies to choose from with slightly different characteristics. We didn't always have multiple nifty technologies we could use for doing memory. And so it didn't really make sense to have hardware caches as much back then. Okay? But like I say, virtual memory was invented in the 60s, and so the terminology that was created for virtual memory doesn't quite match the hardware caching terminology. So caches have blocks, virtual memory has pages, which are the virtual blocks, and frames, which are the physical blocks. You know, you could also say they're level n and level n plus 1 pages. Okay. You also have another thing, which is swap slots. Frequently, the swap space is divided into slots, which are the same size as pages and frames. Okay, caches have cache sets and cache lines. Okay, that was cool. Virtual memory has page tables and page table entries. So cache lines correspond to page table entries, pretty loosely. Virtual memory really doesn't have a notion of cache sets. You can imagine it's like a fully associative cache. So it has one cache set with all the cache lines in it. Okay, that's your page table. Similar, but not identical. Caches have cache hits and cache misses. Virtual memory has page hits and page faults. Okay. So, and I think part of this is also because of the terminology of interrupt handlers. That, you know, it's a fault. We go back to the faulting instruction and try it again. Whereas a cache miss, we don't really consider it in the same way. We try to handle it on the fly without the program actually having to manually do anything at all. Okay, so you can see the terminology is a little bit different. Does anybody have any questions about these terms? All right. Just it's my same spiel that I always give about this stuff. Make sure you use the right words when you describe stuff. I don't know if anybody's had this experience, this term. I hope not, but it always happens. That TAs will sometimes take off points for misusing terms. That's one of my giant pet peeves, so maybe be glad that we have TAs between me and you. Like, if people misuse terms in explaining things, it's really confusing. These terms have long histories, they have meaning, they have definitions that everybody agrees on, and if you misuse them, then it's really confusing to people. So when we get upset about it, it's because we're trying to help you go in the right way. So anyway, just make sure you understand these terms and understand them and use them properly. Okay, let's see. Yeah, so virtual memory is exactly like caches in that if a program exhibits good locality, then it makes us really happy. And the interesting thing about it, though, of course, is that since our blocks or our pages are much larger than cache lines, the requirements that we exhibit really good locality is actually less critical than it is with hardware caches. But nonetheless, if we exhibit good locality, then we'll get a memory that is the size of the disk for approximately the cost of DRAM, or even better if we're really doing very good locality in our programs. As the process runs, it has a certain number of pages that it is constantly referring to. You'll definitely notice this on assignment 8. It's the working set. We call it the working set of the process. This is the set of pages that I'm using right now. And you can imagine that what happens is the program runs, the working set slowly changes. So I'm working on that Excel spreadsheet and I'm typing stuff into the cells and blah, blah, blah. And maybe I don't have a really giant spreadsheet and it maybe only takes like 2 to 4 virtual memory pages to hold all the data of the spreadsheet. Maybe a little bit more. Then I decide to print something. Well, Excel has to load the printer code into the process address space. And so you can imagine that that's going to cause some page faults when those parts of the program are referenced. And so forth. You can see, I don't know if any of you have noticed this. It's really noticeable on the Mac versions of Office. But you start up some facility that maybe you haven't used yet, and there's this pause in the program. You're generating a bunch of page faults, and those parts of the code are being loaded in. Somebody also mentioned, I don't see him here today, but somebody was mentioning how, well, I have this application, and I'm not using it right now. I'm using other stuff, and then later when I return to it, I notice there's a big pause when I resume it. The process never terminated. It was blocked on input. And so what happened is over time, the operating system was like, you know what, nobody's using those physical page frames. I'm going to reclaim them, and I'm going to swap that all out to disk. And when you resume the application, suddenly all those things have to be loaded back into memory. That takes time. And so there's a pause. Okay? So you see how these kinds of things can affect the system behavior. Anyway, that's kind of an aside. Working set. So, like you say, if the program is good locality, the working set usually fits within main memory. That makes us happy. What we're meaning is that the working set is smaller because we have good locality. If we have really bad locality, the working set is large, and there's no way that it can fit inside main memory. So we have a couple of possibilities that could occur. We could either have a program that's badly written and has bad locality, and so it has a large working set, which causes thrashing. Because what happens is a page gets paged out, but I still needed it. And so eventually I refer to it soon, and it gets paged back in, so this is slow. Or it might have a situation where the working set is a reasonable size, given the program requirements, but the memory is too small. And then again, I can have thrashing. Does anybody know where the term thrashing comes from? Just a little point of trivia. It comes from the noises that tapes make when they're read and written with great ferocity and frequency. That actually is where the term emerged, because it used to be that we didn't have disk backing memory. We had tapes, reels of tape. And so going back and forth, it sounded horrible. So that's where the term comes from. But yeah, basically what happens is when your working set is too large, either because of program behavior or because of limitations on physical memory, the program will start exhibiting the behavior where every access is going to be close to disk cost as opposed to DRAM cost. And so the entire program gets really slow. Again, we really don't see it very much anymore, which kind of makes me sad because it is kind of a neat peek into how the system works. But it used to be that when you would have certain programs running, or maybe too many programs, or you're doing something that was very memory intensive, sometimes you would see the program get really slow and the disk light would just be on. I don't know if any of you have had that experience lately. It's really kind of like, I have a solid state drive in here. I don't care. But anyway, that kind of stuff, that was because programs were thrashing and the OS was simply incapable of keeping up. The virtual memory system was incapable of keeping up. So disk access cost was the primary cost of the program. We have so much memory now, it's pretty uncommon to see that kind of thing. So there is a Unix API that you can use to find out things about this kind of stuff. Get R usage. So that's get resource usage, and it allows you to see a whole bunch of details about your operating system, the statistics of what the process is doing, and that allows you to see how many page faults are there, how many context switches, how many times am I preempted versus how many times did I voluntarily yield the CPU and so forth. So there's some interesting things that you can use there. And it's kind of really, really well-written programs will actually be able to take this stuff into account and modify the way that they behave. But you don't see that very often. It kind of tends to be for really performance-critical systems. Okay, any questions? Alrighty, let's see. So virtual memory is now disk-based, so we can start having some new features. One of the neat things about this is you have programs, obviously are files on disk. Where is our virtual memory stored? Well, somewhere on disk. So we can actually start taking advantage of this. When we want to start a program, instead of actually just loading it in and incurring that cost right away, because we don't know which parts of the program are going to be needed, what the kernel does is it allocates a range of virtual pages. And then what it does is it assigns those page table entries to point to the portions of the file on the disk. So you say, my file is 2 megabytes, so I'm going to cut it up into page-sized chunks, and each page table entry will point to the corresponding part of the file. Okay? And all the page table entries are marked as this page is not in memory yet. So like you say, valid is 0. So what happens, you start running the program at the beginning, and you instantly get a page fault, and it loads the first page of the program code into memory. So it starts executing, and then you hit a page fault when you get to the second page, and it loads the code off of memory for the second page and then starts executing. The reason why we like this is that if, I'm basically only executing like one or a handful of instructions at any given time. Like, let's assume we actually have multiple cores, we have a multi-threaded program. Maybe I'm running 2 or 3 instructions at the same time. So I don't really need all of the program loaded into memory if I'm not using all of the program code right now. And so, like I said, the Excel example, if you're only using a little part of your program to do certain things, only those pages really need to be in memory. Everything else can be paged out, and I can use that physical memory for something else. Okay? So that's one thing that we can do. It's kind of clever. This technique is called memory mapping. There's a function called mmap, which basically exposes this capability to user applications. The kernel actually handles a ton of this stuff for you, and it has its own internal implementations that it invokes when you exec VE a program or things like that. But mmap basically allows you to do some very cool and clever things. In fact, you'll be getting very familiar with mmap on assignment 8. This is what you'll be using to do some of the neat stuff in assignment 8. So like I say here, you have a void star start, which basically says this is the address range, the virtual address range that I want to map, so start and length. You can set protections, so you can say this data should only be readable, or hey, it can be read-write. And then FD is a specific file. So when you open a file, you get an integer descriptor that says this is the file that you have open. And you can say, map this portion of this file into this address range. And what it does is it goes and changes the virtual memory configuration for the process. So you see here, it allocates virtual memory pages and then points the page table entries to the disk file. And so this is called memory mapped I/O for a reason. You are mapping portions of the file into memory, and instead of doing reads and writes, or if you will, freads or fwrites or fscanfs and fprintfs, who's done that kind of stuff in C before? Fprintf, fscanf, that kind of stuff to interact with files. This is like, instead what I'm going to do is I'm just going to like open up a window into the file, and now the file's contents are in memory. And when I want to read parts of the file, I just do a memory access. And the page, the virtual memory system automatically loads that data into memory, and I can just access it. And if I want to change something, I just write to those pages. And the virtual memory system marks the pages as dirty, and eventually it will save that back to the file. So it's a really neat, and it turns out to be an incredibly efficient way of doing I/O. I don't talk too much about this here, but and I don't think I want to talk about it too much, except that if you want to write really high-performance software that does a lot of very fast I/O, memory mapping is your friend. because basically you are getting as close to the actual data on the disk as you possibly can, just leveraging the virtual memory system to load that stuff. You can interact it directly in memory using the caches and everything like that, and the virtual memory system will eventually put it back to disk at an appropriate time. It'll do the writes in a way that's hopefully efficient and so forth. So it's a very, very fast way of doing I/O. There's a reason why most people don't do it, because it's more complicated. But very neat stuff. Okay, let's see. Now, since we can load programs and read-only data, remember we talked about back in week 4, I think it was, about, oh, hey, let me try to target the stack. Let me try to target this or that. Let me try to execute arbitrary code. So I really would like to have some way of constraining memory pages to say, you're not allowed to execute this. This is stack. You're not allowed to execute it. Or you're not allowed to write to the program code. You have to leave it read-only. So all we really need to do is add a few more bits to our page table entries to say, this is what you're allowed to do to this page. And then the MMU can check that stuff for us as well. Okay. Just to give you a little bit of a description of how IA32 works, we have 2 permission bits, read-write, which will either make it read-only or read-write. And then you have a user supervisor bit as well, which says, is this page accessible by kernel code, or is it also accessible by user code, user space? Okay. And so this is actually where the terms user space and kernel space come from, because you have memory that's only accessible by kernel mode code, that's kernel space, and memory that's accessible by user mode code. That's user space. Okay. Kernel mode code can access kernel space and user space. That's allowed. User mode code can only access user space. And so this is one easy place to configure that stuff in the page table. Now you'll notice that there's a couple of things missing. I mean, we don't have an execute bit. I think I talk about this in a little bit. But so the current x86-64 specification allows you to set execute permissions on pages as well. Okay, so yeah, like I say here, the kernel uses these virtual memory features for loading and running programs. This was the layout that we basically described, but now we have a slightly different slant on it because you can see program code and program data. Well, some of it's read-only. Constant data is supposed to be read-only, so we can go ahead and mark it read-only, put it in a read-only page. If it's writable data, like global variables, then we can put it in a read-write page. Stack and heap, we can say it's read-write. Obviously, it's going to be local to the process, so those will be physical pages only mapped to that process. Shared libraries, read-only. It makes sense to make them read-only. And they can be mapped into multiple processes, so we'll have multiple page tables referring to the same physical pages, but the pages are marked read-only. Kernel code, kernel data, and process-specific data structures, all of those things will be supervisor-only, so it's kernel space. And obviously the kernel can set whatever constraints it wants. Typically it leaves them read-write because it's the kernel. You know, if the kernel misbehaves, everybody's screwed. Okay, let's see. So since we now have permissions, we have a new kind of fault that can occur. And it's kind of unusual that it is a fault because it means that if we have a permission violation, we could go ahead and try to resolve it. And it turns out that being able to resolve protection faults also gives us some great power. You'll also see this on assignment 8, so that's kind of a cool thing. But the kind of fault raised in this situation is not a page fault because it's for a different reason. So it's a general protection fault. And again, the kernel has a handler for general protection faults, and typically if the user process is what does it, like it tries to write to program code or something invalid like that, it tries to access kernel space, the typical behavior is the kernel will simply kill the process. There's no point in allowing it to continue. Now, any questions about any of this? Our model is pretty rich now. It turns out that it basically covers everything that we need to cover, so I want to see if there's any questions at this point. Okay, so what we're going to talk about now is a couple of implementation issues that we've kind of ignored. We drew this picture. And the picture is like nice and clean. Okay, the MMU accesses a page table, and it uses that to access main memory. So the question is, where do the page tables actually live? Well, they also live in main memory, right? So, what is the potential cost of accessing memory now? Notice I say I want to access a particular address. The MMU has to turn around and look up something in the page table. The page table is in memory, so I have a second memory access being performed. Basically, I could easily double the cost of all of my accesses because I now have to do a lookup in a page table. Why would this be a problem? Because memory is slow. So, like I say here, we basically get a doubling in cost. Ideally, the cost being doubled is L1, cache hit cost. Okay, so maybe we're talking on the order of a few clocks. That would be great, but nobody wants their memory accesses to be slower. So what the MMU does is it involves the most performant or the highest efficiency caching on your processor. It's the translation look-aside buffer. Basically what the MMU does is it realizes, well, if programs are exhibiting good locality, I'm going to be looking at the same page table entries over and over again. So what I'll do is I'll take those page table entries that I retrieve from main memory and I'll load it into the TLB, the translation look-aside buffer. And now when I have an access come through, I can just check the translation look-aside buffer to see if it's in there. And if it is, then now my memory access is much faster. Okay? The TLB typically is like, I can't remember, I think it's like 1 clock for hits. So they try to make it as absolutely fast as possible. Okay, so like I say here, the translation look-aside buffer stores page table entries. So what does it use for lookups? Well, it uses virtual page numbers. That's what we need for the page table anyway. And if you have a virtual page number that appears in the translation look-aside buffer, you get back the page table entry for that virtual page. Okay? That's what the TLB stores. And I say it often has a high degree of associativity. I don't think they're necessarily fully associative. I mean, the memory has to be extremely small for it to be fast. And so it might be a four-way fully associative, or four-way. But I mean, yeah, it may have 4 cache lines, fully associative or something like that. So I can't remember. I might have some stats later on. But it tends to be very, very, they want it to be as fast as possible because this has such a profound impact on system performance. Okay, so we'll talk about translation look-aside buffers more next time. But the other question to look at is how large are our page tables? Like I say here, I've sort of described it as if we have a single page table. We take the virtual page number, we look it in the page table, and we pull out the physical page number, and off we go. And remember, we have valid bit, we have permission bits, we have other bits that we have to keep track of. So page table entries aren't free. So how do we actually do this? So 32-bit address space. We're talking IA32, what we've all been programming on all term. 32-bit address space, pages of 4 kilobytes. Well, 4 kilobyte pages require 12 bits of offset to access values at various offsets within the page. The page numbers themselves are 20 bits. 32 minus 12 is 20. That's really easy. Okay. Now, if page numbers are 20 bits, that means we need to have 2 to the 20 entries in our page table. Okay, 2 to the 20 is what? It's like 1024 times 1024, right? Because 2 to the 10 is 1024. I can never remember all the digits after the 1 million whatever. So I just had to like 1024 by 1024. Okay, so each page table entry on IA32 happens to be 32 bits. 20 bits are for the physical page number. There's a bit for resident. There's 2 bits for permissions. And then there's other bits that mean other things. So page table entries are 32 bits. How big is the entire page table going to be? This is really easy, right? It's just 1 million page table entries times 4 bytes. So we end up with page tables being 4 megabytes. So you start seeing that, well, if I have these page tables for my virtual memory system, and I have to have every page table entry for the entire address space, this is really prohibitive. Now I'm starting to lose a lot of memory just to my page tables. Even if I have my stupid hello world in Erlang or what I'm doing CS11, my hello world in C++, and it needs like 1 page to run, and I still need a 4 megabyte page table just to do that. That's ridiculous. Okay. So the way that most systems that do virtual memory, this tends to be the way it's done now. There's actually an interesting variety of ways that this has been done. We actually use a hierarchy of page tables. So we take the virtual address, and of course the virtual page offset is always there. It's always going to be 12 bits on IA32, so we just bring that down. The rest of the virtual address bits we actually split into multiple components that we can use for a hierarchy. And like I say here, the page table base register only points to the first level. And so we use that level to index into the next level. And then we use the next part of the virtual page number to index into the next level and so forth. What this basically allows us to do is turn a dense data structure into a sparse data structure. Because at any level, we can have a 0 for the entry. So page table base register for level 1, it could be like, here's an address, and we go look in the level 1 page table, and the entry is empty. Then we know there's nothing else past that to look at. So we really only have to have entries now for parts of our address range that are in use. Which means that we now kind of have a tree, and so we can say this part of it we need to look in, and then in there we only have a few entries, and then in those we have a few entries. So now we can have a much finer control over what parts of our page table we represent. It turns out to be far more efficient. So this dense data structure is now a sparse one. Now I have, k levels. Interesting detail. What happens for each level? Where are these things stored? You remember? These things are stored, yes? Somebody say something? These things are stored in DRAM, right? So for every access I have to do into my page table, every level I have, I incur another memory access. So I can't go too deep. The deeper the more levels I make, the finer grain I can be, but the more memory accesses I have. The highest that I know of is like old Sun Spark chips that would have 7 levels in the memory access hierarchy. That's pretty expensive. I have now 7 memory accesses for a memory, a virtual to physical address translation. Okay, so I already talked about this. Entire page table level I is empty, then I don't allocate any pages for it, so I just say at I-1, the entry is null, or it's empty. Okay, so Pentium family, virtual and physical address spaces are 32 bits. Let's get through this last part. So topmost 20 bits are the page entries, or the page addresses, and so it does a 2-level hierarchy. Level 1 is a page directory, and level 2 contains page tables. So entries in the page directory can either be empty or they can point to individual page tables. And so it's something like this. Bits 0 through 11 are the offset, 12 through 21 are the page table entry, and 22 through 31 are the page directory entry. Okay? So we just have 2 levels here. Okay, so yeah, if we had a simple memory layout like this, 2K pages allocated to code and data, it's not a very large program. And then we have space for the heap, but it's unallocated at this point. And then we have a whole bunch of space for the stack to grow down. This is basically all we need. Okay, before we would have needed 4 megabytes to represent this. Now we have a few entries in our page directory and 3 page tables that correspond to the page directory entries 0, 1, and 8. And we have various entries in those page tables that say these are the parts of the virtual address space that are in use. So you can see that this is a far more efficient way of representing a sparse address space, which virtually all programs actually have. Okay, any questions? All right, just as a last detail here, Core i7 does a 4-level hierarchy. Okay, because we're talking 64-bit now. Now that's 64-bit data bus. We really only have 48-bit of address. It's not a true 64-bit address space, which is kind of unusual. That seems to catch people off guard. There's other processors that have a true 64-bit address space. That Sun processor with 7 levels did a true 64-bit address space. But this is only 48 bits. And so, again, we pick 12 bits for the page offset. So we still have 4K pages. So that leaves, 36 bits for other things. And so we have 4 levels, 36 divided by 4. We have 9 bits for each entry. Okay, so like I say here, each level uses 9 bits, and the virtual page offset is still the bottommost 12 bits. Okay, so there's a section in the book if you're curious about that. So next time we'll go ahead and pick this up, and we'll start seeing how Linux is able to use this MMU mechanism and this whole virtual memory addressing thing to do some really cool stuff. We'll spend the next couple of lectures talking about that. So we'll see you next time.